results that can be explored and explained by theory. And the theorists, because of the quality of the experiments, the theorists are starting to pay a little more attention to the experimentalists' need. We're all friends here on this panel. Every one of the people on this panel is my friend. And I hope at the end of this hour we remain friends. I see my role. I am not, as most of you know, I'm not a theorist. You know, I'm not a theorist's toenail. Actually, I am an experimentalist, and I'm going to play the role of a barbarian experimentalist. You know, all I'm interested in experimenting. How can my experiments be improved with the input from theorists? There's a deep disconnect between theoretical physics and experimental chemists or physical scientists, material scientists. One of the manifestations of that, an example of how deep that divide is the phrase nuclear ash. As any chemist understands, combustion of hydrocarbons proceeds with the production first of water, H2O, and second to produce carbon dioxide, CO2. So the heat-producing reactions of combustion, chemical combustion, are H2O and CO2. Ash is the oxidation of secondary or tertiary materials that are contained in the fuel which you're burning, or already pre-oxidized materials. So the idea that the heat is coupled to ash is apparently obvious to nuclear physicists, but preposterous to a chemist. Professor Kim this morning said that theoreticians were at the mercy of the experimentalists, and I've got to say that I support him in this. The situation that we find ourselves in is not the fault of the theorists. The experimentalists simply haven't bounded the parameter space sufficiently tightly by good, deep, and broad experiments, and it leaves the theoreticians far too much room to play. And theorists love to play. I think there are several things that we might ask in general. I'm going to ask this set of questions, and I'm going to ask each of the theorists to address this set of questions, and I'm going to keep score. Score is going to run from 0 to 10. Was the question addressed, and was it answered to my satisfaction? I think a score of 3 is going to be the winner on this panel. Not because of the character of the panel, but because of the way we haven't really focused on and set out addressing the questions. Given that the experimental situation is the way it is, and we experimentalists need to step up our game, is it possible that every one of the theories that you have heard this morning is right? Are they all right? Is there some common ground that would encompass the set of theoretical ideas that was presented to us this morning? Is it possible that there is something fundamentally missing, that all of the theorists are in fact wrong? Josh Billings lived in the States, I guess, from 1818 to 1885. He was a comedian largely, but he said, it ain't what a man don't know that makes him a fool, but what he knows that ain't so. And I suspect that something that we think is true is not true. And my personal supposition is that the answer to the experimental situation we find ourselves in is when we manage to surgically excise some knowledge that was taught to us by our professors and is written in our textbooks, and something that isn't. So with that, I'm going to go down through the theory panel. I'm going to give each one 5 minutes. I'm going to be ruthless. 5 minutes, I'll bang my bell at 4 minutes, and I'll double bang at 5, and you will stop. So you get to answer as many of these questions as you like, but remember, I am keeping a score. So with that, I'm going to turn the microphone over to Professor Takahashi to address the questions from an experimentalist to a theorist. Akito.
Thank you, Mr. Chen. Very kind. Thank you, Chen. And according to my candidate here, I answer step by step from question 1 to question 5. Question: what experimental results does the theory seek to address? In a sense, the most important thing is the heat helium for ash exploration and without visible neutron gamma radiation. And personally, I have a different experiment doing the three-body interaction using accelerator many years ago, and observing a very enhanced three-body interaction 10 to the 10 compared to the random nuclear interaction. However, this is not very necessary in today's discussion. So, second question: what is the underlying physical mechanisms? I think the ordering or organization process in condensed matter have something to do with special, probably hitherto unknown nuclear reaction might be taking place. And in a sense, many body nuclear or electromagnetic interactions of neutrons, protons, plus electrons must be treated under the probably the dynamic condition, constraint of condensation, periodical structure, or surface, fractal mechanism, and so on. So that can overcome to clear the Coulomb barrier problem, as a case of my cluster fusion model, and get to the strong or weak nuclear interaction. In that way, we can understand basically the mechanism, but many other complicated things would be existing around those. And the third question: what are the critical assumptions in the case of the tetrahedral symmetric condensate? I am also concerned with octahedral symmetric condition. If we have a vacancy in lattice, we can have an octahedral condensation of 6 proton possible. However, that will happen in surface dynamics at the moment at some special sites, like SNH, I said this morning. However, what kind of sites would be generated by what kind of experimental conditions? We don't know exactly. That's a big problem. And so the fourth question is, how well does prediction compare with the experiment? I think the ash problem is 23.8 millimeter helium generation would be okay with my model for ODTSC condensation and multiple diffusion. And another important one is according to the Ceramics demonstration over there, and also experiment and so on. The nuclear hydrogen system looks producing very persistent or sustaining high density, high energy density heat we are observing. So to explain that, I will start to propose the hydrogen ESC condensation and strong, weak, strong, almost simultaneous interaction to have a product of helium-3 and neutron as ash without producing not significant or very weak, very weak neutron gamma. So that's possible. So that's the prediction by 1 minute.
1 minute.
1 minute. Okay. This question is what experimental tests can be performed to falsify yourself So that means I felt private by prediction. So if we don't have a helium-4 heat declaration, or helium-3, break with heat, I will be failed. And time dependent astotic effect we have seen, I'm going to explain. If I get failed to explain, I'll be called falsified. And with the, for example, possible pre-emission process with the fall, either capture when possible transmutation or fission fragmentation. What kind of thing?
Thank you. I've given you an extra point for more or less keeping on time. Professor Kim.
First question, you can read on the top, so I don't read it here. I am trying to address all different types of confusion based upon general formulation of optical theory. That formulation allows me to apply to situation, and formula is very general. You have to assume Schrödinger equations, Hamiltonian, whatever program you have, one can assume some Hamiltonian and then solve the program. And that applies to all fields of equations. Second question is essentially again the physical mechanism is different for different areas of field. Nevertheless, one can formulate using the same formulation developed optical theory formulation. What are the critical assumptions? Assumptions will depend on different types of correlation looking at. For instance, Fleischmann-Pons effect. We did assume both Einstein condensation state or something similar, and then solved the equation, came up with the number of prediction, and so on. Number 4. Well, as far as Bose-Einstein condensation nuclear fusion theory is concerned, it can explain about 10 different experimental observations and make predictions which can be tested. And I'm waiting for experimenters to really pay attention and try to do the experiment proposed. Finally, what experimenters can be performed to confirm falsify the theory. I do have a set of proposals to experimental people or group here. In particular, for instance, I have an idea of determining whether deuteron in the metal can form the Bose-Einstein condensate. This is regardless of cohesion, the more basic physics question. And if so, it can have superfluidity. So my challenge to you is to measure superfluidity of neutral metal. And in fact, Dr. Iomura and other group you heard the other day, I was talking to them whether they could do experiments. They were very much interested in experiments. Now that would be a more fundamental physics experiment. So it's important.
Thank you very much. Professor Hegelstein.
Well, the first thing on my list is the absence of energetic particles correlated with the energy produced. As a general statement, past that I was starting to itemize the different experiments. Planck's experiment, Antel experiments, our experiments, Gauzy, Carter, Lentz, Jelani. Wow. I'd like to address them all. In terms of the theory, I sort of view it as two theories. There's the conventional theory that has to do with trying to figure out loading, dependence on temperature, dependence on current density, that kind of thing. And then the new effects, new physical effects, which involve fractionation of the quantum. And the goal is to try to get a computational engineering theory together. Underlying physical mechanism, well, there are two. One is a new relativistic A.CP nucleus moves. When it moves, it tries to get compatible with the Lorentz transformation, which involves mixing with excited nuclear states. And that provides a coupling between motion and internal nuclear states. The other is the sequential interactions of single photon exchange iterated many times while maintaining coherence to fractionate a large quantum. The critical assumption from my perspective is that existing physical theory is very rich and contains what we need to understand the field if we're smart enough to make use of it. How well does prediction compare with experiment? Well, in the last 281 versions of the model, globally, experiment didn't compare very well at all with theory. With the most recent one, I'm getting some measure of quantitative agreement in connection with the correlated X-ray emission with respect to excess heat in SRI experiments and Lentz experiment, Antel experiment. What I can say at this point is the latest version of the model seems to be compatible with the experimental parameters as I understand them. The experimental tests, well, there's to test the theory, the best part of the theory at the moment that's most relevant, can be most tested objectively, would be in a controlled carbon experiment where we would vibrate a sample, have mercury implant or co-deposited on the surface, look to see if correlated X-rays come in, and then study it. That would provide a wonderful platform for comparing quantitatively between experiment and theory. Past that, I have a wish list that would make Santa Claus groan that includes measurements for helium-3 in light water experiments. That includes doping nuclear M4 nuclear transition isotopes into the nickel for nickel hydride excess heat experiment to see if we can get them to radiate in the gamma region on command. Another one is to do a magic angle NMR experiment to look to see for molecule formation in connection with vacancies. Positron annihilation experiments to check electron densities for vacancy formation in high current density co-deposited substrates. And also in Jelani's samples, and a very large number of other tests that I want to see. Thank you.
Thank you very much. I'm bringing it with 1 minute left, so when you hear the first thing, you actually have a minute. Thank you for staying under time. Professor Lee.
What I'd like to address is the 3 old tunnels. Tunneling the column area, no neutron, no gamma, and three new patterns. The K capture rates, no heavy electron, and the neutrino energy will not carry all the energy. What is physical mechanism? That's the selectivity of the resonance. Not only select the frequency, but also the damping. The basic assumption is the resonance energy level. The prediction is three-parameter formula, which is much better than the five-parameter formula I presented in ICCF-17, Washington, D.C. Now this formula is further reduced to two-parameter formula. You see, I predict 6 major reactions here. Now that's the seventh for the lithium-6 plus proton. Need only 2 parameters to be such a good relationship. Finally, the fatal test would be if there is no resonance. Frankly speaking, I don't worry about this because the 3D reaction is based on the resonance with long lifetime. Professor Kasagi, Professor Takahashi discovered this 3D reaction, and Naval Research Laboratory confirmed this 3D reaction. The other thing is that if there is no neutrino emission from our cell, then I will be failed. Thank you.
Thank you. Professor Muhlenberg.
Okay, I've sort of got one model that extends over a lot of territory. It started with the Lochon model. I just go down and sort of hit the models. It shows how we overcome the Coulomb barrier. It uses the polarization of the hydrogen atoms in lattice, D plus and D minus. Shows the lattice phonon field interaction. Looking for harmonic resonances, there's some correlation, coherent correlation effects. And it does predict the cold fusion cross sections, but it's making some assumptions that are actually in agreement with those that are being used right now for the low energy DD experiments. The second model depends upon something that is sort of in agreement with everybody in the theory and practice here. It takes deep electrons to get around the Coulomb barrier. And so we're getting the nuclear proximity from that. We're looking, in our case, because of the polarization, we're looking at Coulomb attraction rather than repulsion. This gives us not just screening, it gives us attraction and super screening even at the end. We're looking at the validity of the relativistic Klein-Gordon and Dirac equations, the relativistic effects, and that becomes very important because this predicts high fusion rates and even transmutation. The extended Lochon model allows us to achieve low or no fragmentation of the helium-4 excited nucleus. It also allows us to lower the Q in the DD to the helium-4 reaction. The nuclear mass is the source of the Coulomb potential energy, and improve that are going to be in publications outside of this field. And it explains all the fragmentation ratios, low neutrons relative to tritium, low tritium relative to the helium-4. And it explains then using the femto atoms, we're able to go ahead and explain transmutation. It depends upon the deep Dirac orbit, and it establishes actually new quantum, it's called nuclear chemistry. It depends upon having femtosecond or even microsecond lifetimes of these femtoatoms. But I think these are realistic if you have high angular momentum states to keep the combination from happening. And it also predicts the only thing we've worked out so far is the energy of the nickel hydrogen system, but it seems to fit the others. I'm going to go ahead and quantify those later. So then the last thing is the energy coupling between the excited nuclei and femtoatoms. This goes back to work that actually Peter and I and KB Sinha were involved in, which is the near-field interactions, electromagnetic interactions. What this does, it allows us to show how the excited helium core can go to ground state without having to have any energetic interactions. What it's doing primarily is ionizing the nearby palladium atoms, the electrons from them. The only thing it uses, it assumes, is Maxwell's equations. And one of the outcomes of this is that it actually explains the helium-4 process, but it also shows how these femtoatoms are attracted to excited nuclei more than to stable nuclei. So this selectivity becomes extremely critical in terms of explaining transmutation and the suppression of radioactive decay products, which is the one thing that has not been explained so far, or one of the several things that have not been explained. But if you're creating transmutation, how do you get rid of all these radioactive decay products? And this gives us an alternative path, so the natural radioactivity is suppressed before it actually occurs. This explains Rossi's comment that you only have radiation at the beginning. Once it's established, you end up with such a flood of these femtoatoms that they go ahead and neutralize the radioactivity that's generated in the transmutation process. So at this point, I think we've explained all the data, principal data anyhow that's been observed. We simply haven't yet gotten down to explaining what molecular structure is necessary to do that. However, I will make a comment on a paper that's going to be given tomorrow that there is a process that appears to avoid the NAE. The NAE, I believe, is a catalytic process that allows you to have results at low room temperatures, but if you have excitation, I think you can excite structures that are not involved here, so there are many more structures that we can solve in different mechanisms. Thank you.
Thank you very much. And last but not least, Professor Bizonsky.
During approximately 3 or 4 years, we have studied the problem of suppression, well-known problem, suppression of action, negative action of Coulomb barrier. There are, of course, different methods of such suppression, but from my point of view, what's most interesting is connected with the using of a new form of the matter, so then coherent matter, coherent state of matter. It is not usual matter because traditional matter that are in the world, it is not coherent because the process of relaxation takes place in any case. In the case of coherent matter, they are possible to create absolutely new properties. For example, it is very interesting, possible to use the fluctuation and the creation of giant fluctuation, where the magnitude of fluctuation by many order more than the average, different average values. My question to my answer to such question is following. For first question, what experiment result does the theoretic to address? I think that all experiments with controlled periodic action to the different system, with totally controlled, is very important. It's maybe action of different ultrasound, infrared action, laser action, microwave action, but in all cases, all conditions might be precision measured and controlled all the time. Only, it's, for example, when we have analyzed the experiment of Little and Finkelstein, it is very interesting, easy for me because all data were presented. But when we have studied some models for Rossi, explanation of Rossi experiment is very hard because it's all totally under the top secret. So, second question, what is the physical mechanism? Okay, physical mechanism, in my opinion, in the area of my investigation, is connected to formation of coherent correlated state of matter. By this mechanism, it is possible to very strong, very high, very young, increasing the probability of under barrier action. For example, increasing by this method is possible in ADF, maybe increasing the gamma exponent by not several times, by 10 power 10, 10 power 100, 10 power 1000 order of magnitude. A fantastic increase is possible. Next one, what is the critical assumption? Of course, there is some critical assumption for experiment. According to this our theory, based on the some initial position. First of all, we have used the harmonic approximation. Of course, it is necessary using not very intensive method of action, because for increasing of intensity of action, harmonic approximation will be not correct. Also, for a long time, very important problem was the action of different stochastic fluctuation. But last 1 year, we have studied the action, the process of fluctuation and damping in quantum mechanical system on the cross-formation correlated state. And now this result is very close to finish, and the article with this result will be published in September in the magazine Journal of Theoretical Experimental Physics. It was shown that action of fluctuation may be suppressed at special conditions, very special conditions. And what experiment test can be performed for that theory? I think that all experiment for once more maybe repeat with the same answer. I need or our team need experiment with totally controlled conditions, totally controlled without any experimental assumption, controlled in relation to the effect frequency. We need the precise frequency, magnitude of action, region of action, change of temperature, all parameters. That's my answers.
Thank you all. That went far better than I anticipated, actually. Now, I propose to ask each of the panelists one short question, hopefully a short answer, mostly to satisfy my own curiosity. So I'm going to use this as an excuse to get information that I'm looking for.